So we're going to be talking about chemical equilibrium, and that's our next unit. That's our new unit, I should say. And we want to kind of get our feet wet, understand what chemical equilibrium is, and what are the basics of it. So, well, where do we start? I want you to start by thinking about an ice cube. No, I actually meant ice cubes, plural. There we go, ice cubes. And with ice cubes, what do we know about ice cubes? Well, we know that ice cubes will melt, and when they melt, they turn into liquid water. And we also know that liquid water can evaporate and turn into a gas. So we could write that in a chemical reaction kind of way, although we're not really talking a chemical reaction so much as a physical change of solid going to a liquid going to a gas. The other thing we know is that when that water vapor is up in the sky, it can recondense in form clouds. Those clouds can send down rain, liquid water again, and if it gets cold enough, then that water can freeze. So we could also say the opposite state changes are possible, that gas can turn to a liquid, can turn to a solid. Now, if we apply that and extend that, we're going to have to know that all physical and even all chemical processes are reversible. And that's one of the key things about this unit, is this idea of reversible processes. Now, we can actually handle physical processes being reversible pretty easily because we can look at water. Chemical processes are a little bit different. And the reason that for us, chemical processes don't seem reversible very often is because we're usually in an open system. We'll talk a little bit more about that in a minute. But if I take that water and I put it in a closed system, so let's say I put it in a water bottle that has a lid, and I let that sit for a while, a closed system, no transfer of mass, is going to start to look like this, where that water that was in the bottle does actually evaporate and starts to collect, and then it can recondense on the sides. So we can still have that, and you'll notice that I've got this double arrow here saying that the reaction can go from the reactants to the products. It can also go from what I would traditionally label the products back to the reactants. Now, we're not going to change what we label, all right? This is still the reactants and these are still the products, but it's possible for the products to convert into what we would traditionally label as the reactants. So we're going to still talk about reactants and products. We're still going to talk about the reaction going to the products, but it can also go to the reactants. If I had that water bottle, well, some questions I would want to start to ask. A, how much water would evaporate? And you might be thinking of an answer. How much would recondense? And if you think about that picture, the droplets that you could see on the inside, that was the water vapor that had recondensed. And then how much of it would still be in the vapor form? And then finally, and actually kind of more importantly for later, is what if I put that water bottle in the fridge or I put it out in the sun? How would that influence this thing, this liquid to gas back and forth thing? If I put it in the fridge, would more of the gas convert to a liquid? Would those droplets get bigger? If I put it out in the sun, would more of the liquid evaporate and turn into a gas? And maybe those droplets would get smaller. Think about that container. Now, not really a water bottle, although it could be because I can't really draw a water bottle. Put some water in it, liquid water, and some of that water is going to evaporate. Now, it's possible that that water that has evaporated will recondense into the liquid state, but if my lid is off and my system is open, that water can also escape, and eventually the water will leave that container into the atmosphere. And that open system is normally what we work with in chemical reactions. We often have reactions where it is open to the rest of the surroundings. Put a lid on it though, or seal it. Now any water that evaporates is also going to be able to reconvert back into evaporates into a gas, can also turn back into a liquid. And I'll have that point where no matter how long I look at this thing, the level doesn't change. Now, even though the level doesn't change and it appears that nothing is happening, there's this constant movement of water from the liquid state into the gas state and from the gas state into the liquid state. And there's that constant motion. But because the amount going into the liquid, I'm going this way, the amount going into the gas state is going to be balanced by the amount going into the liquid state, the level doesn't change. So we set up this thing, and that we're going to start to use the term an equilibrium. So whenever we see this double arrow for our reaction, we can talk about an equilibrium. And the reality is all chemical processes, because that's going to be our focus, all chemical processes will tend towards equilibrium. Whether or not they can actually get there is another case. So equilibrium for us is the point at which the change seems to have stopped. Physical change, chemical change. Again, our focus will be chemical change. Seems to have stopped. It's a balance point, but I want to emphasize that it's not a mass balance. It's not a concentration balance. It's not about whether the moles per liter are equal on either side, or the weight of water, the mass of water, if liquid and the mass of water vapor are the same, or volumes. What it is it's the point at which the rate of forward reaction, so water evaporating, is equal to the rate of reverse reaction, so water recondensing. When those rates are equal, then I have equilibrium. So just as fast as it's going forward, it's going reverse at the same speed. We'll sometimes talk about a dynamic equilibrium. And dynamic just means that it's still moving, it's still happening. So it doesn't appear to be happening, but there's a lot of stuff going on. We just can't tell. All right, so let's get into the real meat and potatoes, the real important stuff for what we need to do in order to move forward with this. We're still going to label reactions as reactants and products. All we're really doing is, on paper anyhow, including a reverse arrow. We want to be able to start to understand how far that reaction goes, or in other words, the extent of the reaction. So traditionally, we thought that the reactants go in and they make the products. And when the reaction is all finished, all of the products are consumed. Now, we're at the point where that's not the case. Some of the reactants are still there because some of the products have converted back into reactants, and those reactants might react to make more products, but then at the same point, more products will be reacting to form reactants. It gets kind of weird. So we want to figure out how far the reaction goes before it reaches equilibrium. And we're going to use this thing called an equilibrium constant. Now, I'll either use K or Kc, and the only thing that we use Kc for, although sometimes you'll see a Kp, is if I'm using concentrations, moles per liter, or if I'm using pressures for that special case of where I'm talking about gases at equilibrium. And Kc as a constant is going to be the concentrations, okay, so if it's Kp, be pressures, but the concentrations of products divided by the concentration of reactants. Now we're going to tweak that in a couple of minutes, so don't get too wrapped up about that now. Let's just understand it first. And if I have that value of Kc, or if I have that relationship of products over reactants, and I get a number out of that, then if I have a K value that's larger than 1, and let's say it's really large, it's a big number. What that means is the products are favored. So I have a really large number on top, products, and a smaller number on the bottom. So let's say, I don't know, 10 over 2. Well, that's equal to 5. A number larger than 1 means I've got a bigger number on the top. If, on the other hand, K is small, then that means the reactants are favored. So if I were to look at the concentration of products, maybe that's my 2, and the concentration of the reactants, I still have lots of reactants that haven't made products. So then I have a small number, and this would be, say, 0.2. If K is around 1, and I say around 1 because K can be very, very large, it can be very, very small. But if it's around 1, then that means that, well, you've got, let me go back there, you've got neither one is favored. Okay, now we'll move forward. How do you get that? Well, in order to get the equilibrium constant, you need to have a reaction, and you need to have concentrations at equilibrium. That's going to come up in a minute. I said we were going to tweak the value of K, or not the value of K, the expression for K. This is how we get it. Now, real key thing here, in another area, we talked about rate laws. In rate laws, the exponents were not the balancing coefficients. In equilibrium expressions, they are. So these balancing coefficients, they get used as exponents. And if you really want to, we'll figure out why that is in class another time. In order to get that, as I mentioned, we have to have a system at equilibrium. It doesn't do us any good if it's not at equilibrium. We won't be, we can get the number, but it won't be the equilibrium constant. So let's take a look at a chemical reaction. We're going to use this one. And I'm going to start out with a picture. I'm going to represent hydrogen molecules as these green things, iodine molecules as yellow, and when they react to form hydrogen iodide, I'll be using combinations. No big surprise. So we're going to take our container, and we're going to put in some hydrogen, we're going to put in some iodine. Then we're going to allow them to react. Now, really, well, okay, I'm not going to say really important, but kind of important. What I've done next is kind of arbitrary. So I'm not stating anything about this reaction really. So some of that reacts to form hydrogen iodide, and I've got a couple there, okay? Now, if I were to take this container as a 1 liter container, and if I were to take each little pictorial representation as 1 mole, then I've got 5 moles per liter of hydrogen, 5 mole per liter of iodine, and 2 mole per liter of hydrogen iodide at equilibrium. Started out with more and less, depending on if I'm talking about reactants or products. But at equilibrium, right, so if I let that thing reach equilibrium, and these were my numbers, well, what would I do with that? I would go back to my reaction, I would write my equilibrium expression, where the balancing numbers become coefficients. The only real balancing number I've got, I said coefficients. The balancing numbers become exponents. Okay? Then, if I took my equilibrium concentrations and put those in, this is what I end up with. Now that number, you'll notice, of course, is less than 1, and as we saw, it favored the reactants. So there's still lots of hydrogen, lots of iodine left. Okay? That's not the point. The point is, this is how we find our value of K, or Kc, and this is how we use it. If you don't know that the system is at equilibrium, you can't call it a K. You can't call it the equilibrium constant if you don't know it's at equilibrium. However, you could find what's called the reaction quotient. Well, what's the reaction quotient? The reaction quotient looks a lot like K. In fact, the expression is the same. The difference is this is for a system that's not at equilibrium. Well, what if the system were at equilibrium? Well, if the system were at equilibrium, then QC is equal to Kc. In other words, if I take a reaction and I find the concentrations at that instant and I figure out the value of Q and it happens to be what I'm expecting equilibrium to be, then now I know that reaction is at equilibrium. We'll spend a little bit more time with Q at another time. If Q is larger, okay, now we already know what that means. That means we've got a large number on the top and a smaller number on the bottom. If Q is large for what it should be, that means that I've got more products than I'm supposed to have, so products have to convert to reactants. That means the reactants are going to be favored. That means it's going to push toward, in order to reach equilibrium, it pushes toward the reactants. Less products will be formed, so less products will be there. Let's put it this way. Products are going to have to convert to reactants, and that way my Q value will go up. If Q is smaller than K, and we know how that works as a fraction, big number on the bottom, little number on the top, in order to get the point where Q and K are equal, I've got too many reactants. Those reactants are going to have to react to form products. As a basic starting point, that's what we have. So we hopefully understand what an equilibrium is. We hopefully understand how to write an equilibrium expression and how to, where to get those numbers or what numbers to use and what to do, what to call it if we don't know if it's at equilibrium. Okay. Anyhow, we'll talk to you in class.